Welcome to this explainer. If you're a college student deep into your coursework right now, or honestly just someone curious about how the world actually works, just take a deep breath and relax. Today, we're not going to look at chemistry as some stressful series of equations you have to memorize. Instead, we're going to explore the quiet, almost invisible architecture of our world. We're looking at the hidden strength in everyday materials, taking a calm journey into how simple, microscopic connections build the incredibly durable reality we live in. So, have you ever actually wondered where everyday materials get their hidden strength? Think about the stuff you literally interact with every single day. The durable textiles in your backpack, the flexible tubes under the hood of your car, or even those tiny, resilient mechanical gears inside your electronics. We almost never stop to ask how they withstand so much wear and tear. Well, the answer lies in chemistry, but wait, not the kind that keeps you up at night cramming before an exam. It's actually this beautiful, structured process where molecules just reach out and hold on to one another.
Okay, let's dive right into Section 1, the building blocks linking hands.
To really understand this hidden strength, we first need to zoom all the way down to the microscopic level. What are these materials actually made of? At the heart of all this durability is a process called polymerization. I know, it sounds a bit intense, but let's just break down the roots of the word. In Greek, poly simply means many, and mer means units. So a polymer is really just a macromolecule, a massive molecule, made by linking together a huge number of smaller, identical molecules called monomers. Imagine one single person standing alone, right? That's your monomer. Now imagine 100 people linking hands to form a long, unbreakable chain. That chain is the polymer. In chemistry, we use the phrase degree of polymerization to describe exactly how many of these smaller units are, comfortably holding hands in that chain. If 100 ethylene molecules link up, boom, your degree of polymerization is 100.
Moving on to Section 2. There are two ways to build: addition versus condensation.
Now that we're clear on building chains, how do they actually come together? In the polymer world, there are two primary ways to convince these smaller monomer units to link up and build something larger. Let's look at the first method, addition polymerization, which is also known as chain growth. Looking at the top part of our visual here, we see ethylene molecules. In this process, the monomers have to have a double bond. Once an initiator kicks off the reaction, it rapidly breaks those double bonds, letting the monomers basically snap together in a lightning-fast, self-adding chain reaction. The final result is an exact multiple of the original monomers. It's an incredibly fast, highly exothermic process where literally every single atom from the original monomer is used. There are absolutely no leftovers. Zero.
Then we have the second method, which is called condensation polymerization, or step growth. If addition polymerization is this rapid, snapping chain reaction, condensation polymerization is a slower, much more deliberate handshake. Here, the monomers aren't relying on breaking double bonds. Instead, they have reactive functional groups at their ends, kind of like specific puzzle pieces. When these groups meet, they bond in gradual steps, but because they're forming a brand new, highly stable connection from these complex groups, they absolutely have to shed a tiny, simple molecule just to make the pieces fit together seamlessly. This byproduct is usually something super simple, like water or hydrogen chloride.
And this brilliantly illustrates the core differences we were just talking about. On one side, we have addition, requiring multiple bonds, acting rapidly, forming exact multiples and leaving nothing behind. It's literally like zipping up a jacket in one quick motion. On the flip side, we have condensation, requiring reactive functional groups, building in slow, steady, gradual steps, and always eliminating a simple molecule, like water, as a byproduct. Understanding this difference is absolutely crucial, because the way a polymer is built fundamentally dictates how it's going to behave out in the real world.
Which brings us to Section 3, creating Nylon 6,6, a perfect handshake. Let's see how this deliberate, stepwise chemistry creates something tangibly powerful that we use literally every day. Here is the actual recipe for a very famous condensation polymer, Nylon 6,6. It's made through the condensation polymerization of adipic acid and hexamethylenediamine. Now, you might be wondering, why the name 6,6? Actually, it's wonderfully simple. The first number just refers to the 6 carbon atoms found in the diamine, and the second number is for the 6 carbon atoms in the diacid. When these two specific molecules meet in the absence of air, they perform that deliberate handshake we just talked about. They link up, they drop a water molecule as a byproduct, and form a polyamide chain. It's just this beautifully balanced, perfect molecular handshake.
And now, Section 4, strength in the real world, the macro result.
So what does this all mean for us? How does a microscopic handshake actually affect our day-to-day lives?
Well, because of those strong, deliberate condensation bonds, nylon 6,6 becomes a highly stable, translucent, and high-melting polymer. It has incredible thermal stability and abrasion resistance, meaning it can take serious heat and physical wear without breaking down. It's even insoluble in common organic solvents. Because it's so exceptionally reliable, engineers and designers put this stuff everywhere. I mean, it's a huge staple in the textile industry, but its sheer strength also makes it perfect for mechanical gears, bearings, and machine parts that deal with high friction. It's the exact reason the zippers on your overstuffed college backpack don't just immediately snap, and why the casing of your laptop charger can take such a beating. If you look closely at the automotive or telecommunication industries, you'll see nylon 6,6 used for flexible tubing to safely convey petrol or acting as super tough electrical insulators. It's pretty amazing how we can seamlessly connect that stable molecular structure to the physical durability required to keep our modern world running safely.
As you head back to your studies or just your daily routine, I really hope you take this calm thought with you. Immense strength and durability don't always require chaotic, high-energy explosions. Oftentimes, the most resilient things in our world, just like nylon 6,6, are built through deliberate, simple step-by-step connections. Whether it's the molecules forming the parts of a car engine or the daily habits you're building for your own future, strong things are built one simple connection at a time. Thanks for joining me for this explainer. As you head out today, take a look around and ask yourself, what other invisible, everyday connections are quietly holding your world together right now?